Alright, welcome everybody to week 3, day 1 of everyone's favorite discrete math class, Seaside 26. And I was just playing for you was Rainbow, of course, live in Cologne. We should talk about the RSA assignment. So let's go ahead and see what's going on with that. So for the assignment, this is using the Boost multi-precision library rather than including the whole thing, which slows your compile time down even more. We're just using the parts of it that we need, so it's nice they split it into different headers. It still takes a really long time to compile though, so I've found that every time I use Boost, the compile times just tank really badly. It's one of the downsides to using templates. You know, it's maybe one of the downsides to C++ is their build system is a problem. It's a problem. -03 doesn't work, have to use -01. Interesting. This code compiles though, right? Look at that build time. Super fast. -03. So it's the problem you're seeing with -03 Yox timer. If your code's running differently with -01 and -03, there's probably a problem somewhere. It throws an error on read option. Yeah, it's because you have to compile with C++ 17 or above. So if you do this thing where you're like unaliasing it, G++ by default is up to C++ 14. And so you have to do a stud equals C++ 20 or 17 at a minimum. When you compile it and it tries using read optional, it'll actually say right here, use stud C++ 17 to compile. So that, yeah. So -- stud equals C++ 2a, and it'll work fine. Does the compile time change if we were to use makefiles? No, because it's just a single file. Makefiles will not help with this. Almost all the compile time for this project is not in this code. This code is only 144 lines of code. It's the inclusion of Boost is what's causing it. So if you wanted to speed up the compile time, what you would have to do is have main include Boost. Nah, I don't really see any way of doing it actually. You'd have to, like, there's a way of like passing a pointer to something, and then you, in a different file, you take the pointer and work with it. But in this case, that other file would need to include the Boost CPP end anyway. So yeah, I did that with like the image processing assignment. I split it into 2 different files so that it would go from like a 13-second compile time down to like instantaneous. So that is actually one of the nice uses of pointers. So this is 2,000 lines of code, and so when you include Boost CPP int class, it then also transitively includes all of this stuff, and so you end up with thousands and thousands of lines of code that need to all be parsed. Using precompiled headers helps with it, but only a little bit. Basically, every time you're compiling your code, you're going through thousands and thousands of lines of code, which, again, it's probably one of the biggest downsides of C++ right now, is that the build system is just completely like CPP int isn't changing, you know what I mean? Like it's fixed. But it still has to parse all those thousands of lines of code anyway. So modules is coming. Modules is technically out in theory. It's not, however, supported on the compiler on our server. So modules has, at least in theory, a better way of including files. So it's more of a Java way of importing things, and it may improve build times, but it's still sort of up in the air how it's gonna shake out. So See how it goes. The irony of calling a library called Boost, it slows down. Yeah, Boost, you know, every time I've used Boost, I just noticeably, like, the compile times just tank. In a makefile, you can include the needed library to reduce compile time. Makefiles aren't going to help with this. It's not a scenario that makefiles help with at all. Makefiles help when you have multiple source codes, .cc files, .cpp files, and so if you have 50 .cc files, a makefile will be like, all right, this one changed, let's recompile it and not the others. It doesn't help in the case where you've got one file and it just happens to be including 10 times more code, 20, maybe even 100 times more code than is in main. All right. Can you explain what we need to do in the generate function? So, yes, I'm going to go through the RSA in more detail right now. What is the compile flag? Plus compile flag show includes. It's like dash. It's not capital I. That's to find the include directory. Preprocessor options dash. What is it? Dash E. C++ dash E. .cc. There we go. All right. Yeah. So after we're done including all of the headers and everything, we started off word count dash L is the number of lines. So we started off with 144 lines of code. By including all the Boost stuff, we end up with 202,000 lines of code. So yeah, it's expansive. It is an expansive include. And when they're templates, you can't precompile them, right? And that's again like one of the problems. And so maybe you could instantiate a template and then link against it or something. But yeah, this is one of the downsides to C++. And it's not like the committee's not aware of it. Like they've been trying to figure out, you know, package management. If you've ever used Python or even JavaScript, you'll know that if you need something, you can, if you need something installed, you know, it can just automatically download it and install it. And yeah, C++ has no standardized way of doing that. There's something called Conan, and there's Maven and some other things that'll do that. But yeah, the whole compilation process it's messy. It's really messy. Pip 3, yeah. Mm-hmm. Yep. All right. Complaining over. So, somebody asked, how do you initialize an int from a string? You do it like that. All right, so let's go through the different functions you need to write. You need to generate, encode, decode, encrypt, decrypt. You have to do all of those, I think. So for generate, we are going to read, yeah, that works just fine. So, so when you do this, yeah, so you're going to read in a number like 10, and then you need to return the next prime number bigger than 10. And to do that, you're going to use the Miller-Robin test. Okay, so the so I'd like for you guys, I kind of don't want to just like give you the answer here because it's one line of code, right? So I kind of don't want to just give it to you. So I kind of want you to go through the docs and things like that and figure it out, because you're third semester computer science students now, and one of the core skills of being a successful computer science major is you need to be able to look at documentation, look at example source code, and adapt it for your own needs. So this, yep, this one here has everything you need to know on it. I'm not going to give you the line of code that does the primality testing, but it's on there. Okay, it's one line of code. And so what you need to do is when the user types in 10, you check to see if 10 is prime. Well, it's divisible by 2, so it won't be prime. And then you go up to 11, and if 11 is not prime, which it is, then you go up 2 to 13, and if that's not prime, which it is, you go up 2 to 15, 17, 19, 21, 23. You go up 2 at a time, because only odd numbers can be prime, right? And I mean, technically you could test every one. It's just all the ones you test that are divisible by 2 are pointless. So what you're going to do is you're going to call Miller Robin over and over again until you find a prime. And so at whatever number they pass in, 1,000, you check to see if 1,001 is prime, 1,003 is prime, 1,005 is prime, 1,007, and you just go up the line that way. Okay. So, you guys understand for the finding primes, and then yeah, this is the FMT format library, which is a new way of printing things out that was included into C++ 20. It doesn't work with CPP ints, and I've gotten it to work before, which is really frustrating. I just don't remember what I did. So there's like FMT has like an OStream library in it, and CPP int has an OStream double left arrow operator thingy. So it should work, but I don't know. I didn't play with it that long. I have gotten it to work before, but it doesn't matter. This I just put this in here to show you that there's an alternative to using cout. So this is a new way of doing cout, and if you look at it, you'll see it's a little bit more compact than the cout way. It gets rid of chevron hell. That's what they say. So what this says is it's going to print P to the screen, and it substitutes in where you have the curly brackets in there. So wherever you put a pair of curly brackets, then it'll, like if you wanted to print P and Q, you can do something like this, like P, Q, like that. And I'll offer you guys extra credit if you can get that to work, because I know you can get it to work. I've done it before. I don't know where my source code is where I get it to work. It's in there somewhere. It's in my source code examples somewhere. I just don't remember the right thing. Okay, so that is your extra credit opportunity for this assignment. Get the FMT library to work, and I think this is yeah, and you'll have to include that as well. Okay. So there's both FMT and there's format. So FMT is a third-party library you install off GitHub. Now in C++ 20, there's just include format, which is close to, but not exactly the same thing as the FMT library. Yep, so you guys all understand? Extra credit available if you can get that thing to work. You guys with me? Okay. So yeah, E is done for you. So if N is greater than 65537, which it should be for any reasonable RSA, then we use 65537. If not, we pick an E that is smaller than N. It's got to be a prime number smaller than N. And then we're going to output E, N, T, and D. N is the multiplication of P and Q. Sorry, N is the multiplication of P and Q. E is done for you. T is the modular inverse, which can be computed using this function here. So you pass in T and E, and it computes the modular inverse for you. Sorry, T is P minus 1 times Q minus 1. Oh Lord, I need more coffee. Okay. Let me just notate these real fast. And so literally all you're going to do, I'll just give you n. You're going to be like CPP n is equal to p times q. There you go. That's what you got to do. Oh, we already have n. Actually, I already declared it there. So, yeah, there you go. That's all it takes. And it's going to multiply two very large numbers times each other. That's how easy the boost multi-precision library is. These numbers can have 300 digits in them. No problem. It'll multiply them together, store the result into n. Okay. So, yeah, boost multi-precision is really cool. The downside is the compile times suck. So, I just don't think it's a priority for them to make it compile quickly. All right, so maybe it is. I don't know. Maybe that's the best you can do. Who knows? So n is equal to p times q. There you go. That's that one. T is I don't want to write the source code for this one, but t is t minus 1 times q minus 1. I'll let you guys figure out how to do that. You guys think you can figure that one out? All right, and then D is the modular inverse. So D is the calculate inverse is the name of the function. Call the function passing in T and E. It gives you D. Okay. So making the primes, generate E and T and D. Okay. Then, oh, you need to figure out how to convert ASCII into big N. Right. So that maybe that's what the student was asking. The student's like, how do I initialize a CPP int using a string, which is this. If you're initializing a CPP int using a string, it's that. But that's not what encrypt and decrypt are talking about. Encrypt and decrypt are using like how do you convert hello world into a number, right? So basically it's pretty easy. You take the ASCII code, like if do you guys know about ASCII? Have we gone over that before? ASCII? Yes, yeah. We're not doing Unicode. We could probably do it actually using the same algorithm. I don't think it would actually change very much, but so okay. So Cheryl, ASCII is the American Standard Information Interchange format. Okay. It's basically what's the best way of putting it? So there's no such thing as like letters inside of your RAM, right? Everything's zeros and ones. And so somebody at some point had to sit down and say, okay, how do we hold the letter A in zeros and ones? Okay. And the ASCII system is sort of a standardized system for holding the English language in the most basic format. It's only 7 bits. It should have been 8, maybe, arguably, but the fact that it was 7 actually kind of worked out in the long run. So how many possible characters can you have with 7 bits? Anyone know? How many possible letters are there in ASCII if you have 7 bits? To the 7th power is 128. Yep, exactly. So these are the 128 possible letters you can have in your emails and print to the screen and things like that when it's in ASCII format. No emojis. Right? So somebody sat down at some point and said, okay, well, we're going to say the letter A is 65. And the letter capital B is 66. And lowercase a, it's not 65, lowercase a is 97. And so they have got the letters A through Z, the lowercase letters A through Z. In between these two chunks of letters, there's some brackets and the backtick and the underscore character. There's reasons why it is this way, but basically the 97 minus 65 is 32. So if you're like, wait, 32, that's a power of 2. Yeah. They made the capital lowercase letters a power of 2 separate from each other, so you could uppercase or lowercaseify by setting a bit on it. So if you know something's a letter, you can uppercaseify it by clearing the bit corresponding to the number 32. Or you can lowercase it by setting the bit. So that's why, you know, there's things in between there. And then if you look at the top end of ASCII, there's the null character. That's how you end a string. For those of you that have never messed with strings before, the old way we did strings was there were an array of characters with a null character at the end of it. The null character is 0. So if you sent 65, 65, 65, 0 over the internet, then the person on the other end would read that as ah, and then the null character means we're done with the string. So a lot of these aren't used anymore. Start of heading, start of text, like all this is all just historical nonsense. Device control 2, like all this could have been used for accent characters, right? We do have accent characters in English, you know, not just in foreign loan words, but they don't exist in ASCII, right? So then you've got less than, greater than, equal to, exclamation mark. So these are basically the characters that you can type with. Unfortunately, the first 32 of them are almost all worthless. Null's used, tab is used, new line is used, and basically the rest of it is just not used at all. Escape character, I guess. You hit escape in Vim, right? So there's a couple of these things that are used, but by and large, all that stuff, honestly, it should have been used for, you know, more practical stuff. But this comes in part from Teletype machines. So a Teletype machine is before there was the internet, there were Teletype machines, and what it was a keyboard that you could type keys on, and it would connect to another Teletype machine, and you could type keys, and it was a teletypewriter. So you could connect to another Teletype machine over a phone line and type, hello, how are you? And they could type back, doing good, how are you? And it was, you know, when you connected to a mainframe back in the day, when you were logged on to the server, you would connect to it with your Teletype machine, and it would be like, please enter your username. And you type in W. Kearney. Please enter your password. Hello. Boop. You're logged in. You know, LS. And it would, you know, that's how people did coding back in the 70s. And it's and these things were actually around for a long time. Like you know, connecting to a mainframe obviously required mainframes to exist, but these things, what year is this? This looks pretty old, actually. Donate negative money. Yeah, Mr. Bell, they still have the JavaScript blocking of negative money. Okay. So the Teletype Corporation was founded in 1928. So think about that. Like, they had basically something that kind of resembles PuTTY in 1928. Right? Like, pretty cool. In fact, if you... What is Teletype? A teletype printer is a communications device, a keyboard similar to a typewriter, It enables you to send and receive printed messages. With it, a written word can be sent instantaneously by wire within the office or plant, or clear across the country to a single destination, or to any number at the same time. In today's business world, in fact, teletype equipment is often more than a communications instrument. It's a basic instrument. So, do you know what PuTTY stands for? TTY, teletype device. It's a play on the word TTY. A TTY is a teletype device. So if you, yeah, like the history of technology is really fascinating because you have technologies built on technologies, built on technologies, built on technologies. And so the teletype device is based on the telephone and the telegraph, right? And so you would have, back in the day, you'd have, people with the Morse code signals and things like that. And then they built machines that would automatically transmit the Morse code for you. And so all of this kind of nonsense you see that we still use to this day, and this isn't even the most modern thing, right? Unicode is. So Unicode, UTF-8, is ASCII for the bottom 7 bits. So if you send an ASCII character to somebody who's using Unicode, it'll draw. UTF-8 uses ASCII as, if the top bit, if the 8th bit is 0, you can send it an ASCII file, and UTF-8 will render an ASCII file perfectly. If the top bit is set, then it looks at the next bit and says, oh, that's a poop emoji. And so UTF-8, which is used by 90% of all websites these days, is backwards compatible with ASCII, who's backwards compatible to a certain extent with teletype devices, which are backwards compatible with telegraphs. And it goes all the way back to like some guy in a room, with a wire, hitting a thing. It's a pretty fascinating system. So how do we convert 65 into a number? Not impressed by the history of that? Because I am. It blew my mind when I first realized that. It blew my mind how long people have been able to, send emails to each other, essentially. Like, we're coming up on the 100th anniversary of it. So how do you convert the number 65 to a number? Do you need me to pause the recording so you can think about how to convert the number 65 to a number? Isn't it a number yet? Yeah, it is. It's already a number. So, right? So for a letter, you don't have to do anything, right? No, not the digits 6 and 5, like the letter A. Let's say they were trying to RSA encrypt the letter A. That's just the number 65. And so you take 65 and exponent it and modulus it. You do the powim function. And that's it. So how do you send the letter AA? That's a little more complicated, right? So if you want to send the letter AA, you have to convert the letter AA into a single number so that you can do the powim function on it. Well, easiest way of doing it is to the tablet zone. Int C is equal to A. I would not use an int. I would use a CPP int. If you use an int, you're going to overflow real quickly. An int can hold rate 1 note for Windows 10. Oh my goodness. I would love to, but not today. Okay. So, yeah, if you have an int, right, an int has 32 bits. And so a char is 8 bits. So an int can only hold 4 letters, right? And so think about it. Like if we were to hold, like if we were to draw an int, it's just 4 chars, right? So we could feasibly store A, B, C, D in a single int, right? Do you guys see that? like you have 8 bits here, and 8 bits here, 8 bits here, 8 bits here. Does that make sense? I'll show you guys the trick to do that in a second. But CPP int C equals A. Yeah, you can do that. So how do you stuff multiple letters in? Well, there is something called the left shift operator. So if you have a CPP int C, and it's equal to the letter A, and then let's say you want to put the letter B into it. Well, what you do is you say C is left shifted 8 times. So what that does, it moves all the bits 8 to the left. So whereas before you had 65 in there, programmer mode 65 is, so when we have the letter A in binary is 0, 1, 0, 0, 0, 0, 0, 1. Okay? So if we left shift it by 8 bits, all these bits go 8 to the left. And you notice they're 8 bits wide. So what happens, it turns into 0, 1, 0, 0, 0, 0, 0, 1, 1, 2, 3, 4, 5, 6, 7, 8 zeros. So when you do this, C is left shifted by 8. And maybe I shouldn't have used the letter C, because it looks very similar to the, the left shift operator. Let's call it M, because that's what we're using for our message. CPP int M is equal to A. M is left shifted 8 times. Okay. And if you're like, well, wait, I thought the double left arrow was the C out operator. You would be both right and wrong at the same time. What Bjarne Stroustrup did was he overwrote or overloaded the left shift operator, which is supposed to move bits to the left, and he repurposed that for transmitting it to the screen. So the C purists hate C++ in part because the bit shift operator has been repurposed to do like reading and writing to the screen, right? And so the double right arrow is right shift. And so if you were to take this and right shift it 8 times, you'd essentially get rid of the bits below there. And yeah, and we use that for CN. Okay. So what does that look like in practice? Yeah. It'll look something like this. CPP int, don't capitalize it for me. CPP int message equals 0, and then in a loop you're going to read one letter at a time. Don't capitalize it for me. You're going to do something like this. I don't know. Char C is equal to read. You read like one letter at a time from the keyboard. You might do CN into it instead. I don't know. It's up to you. However you do it. But you're basically going to read a character at a time, and then the message, the reading of a character at a time. I'm not going to explain to you. Let's put it that way. And then the character is going to be added to the message like this. So if the secret message is hello world, you first read an H. Okay. So let's kind of trace the execution a little bit. We'll start off with M is equal to 0, and our message we're going to be processing hello world. Actually, that's going to take too long. Let's do Hel, the name of Loki's daughter. Cool. It's a little bit weird because in Thor Ragnarok, Hela is Loki's older sister. So, okay, so we're gonna convert Hel into an integer. You guys with me on this? We're gonna do the encoding thing. Okay, so Hel starts with a capital H, which is 72. Okay, so we read in the letter H. Again, I'm not gonna go through how to read a letter. You should know how to do that already. Don't do this if you copy this verbatim, it's going to be an infinite loop, right? You notice how there's no break or anything like that. I'm going to leave that up to you. So it's going to read H. We left shift 0 8 times, so all the bits go left 8 bits, which is 0. We then add 72 to it. So the message is now 72. Yep. Which corresponds to, if you want to see it in binary, is 0 1 0 0 1 0 0 0. So this is another way we could talk about M. This is in decimal representation. This is in binary representation. So we read another letter. We read the letter E. We left shifted 8 times. And so all these bits go to the left 8. And so the number now looks like this. And what is that in decimal, you ask? Well, that is, of course, 18,432, obviously. I used a calculator. I did not do that off the top of my head. So so we left shifted 8 times after. So we've read the letter H, put 72 in there. Now for the next letter, we move the 8 bits out of the way, and we put a new 8 bits. So these bottom 8 bits are going to be the letter E. Okay. So we're now going to add the letter E into this, and the letter E is, of course, lowercase e, which is 101. So 101 in binary is 0 1 1 0 0 1 0 1. Okay. And so this will be 533. Okay. Now we read the next letter. So all these bits shift 8 to the left. Okay. Which I can do very quickly by just putting 8 zeros over on the right. And then this number here is going to be much bigger. 5 3. So 18,533. Oops. 33 left shifted 8 times becomes 4,744,448. Okay. And then we add in L, lowercase l, which is 108. So you see what we're doing? We're moving all the bits we have 8 to the left, then we're taking the new letter and putting those in as the bottom 8 bits. And if there's another letter, we shift everything to the left, put in the new letter as the bottom 8 bits. Shift everything to the left 8 bits, put in the new 8 bits for the letter. And so we're converting a string like hello world into one really, really, really large number. And it gets exponentially big. Okay. So what was L again? 108. So 108 in binary is 0 1 1 0 1 1 0 0. Okay. And so the binary 4744448. Just double checking the binary is all correct. Left shifted 8 times becomes 1,214,578,688. The decimal numbers really don't matter. Basically, we're just treating this as a giant binary number, and then we add in 107 to it. And so at the end of the day, we end up with 95. Okay, so that's the number: 1,214,578,795, and it's pointless to think of it in terms of decimal. because that decimal number means absolutely nothing. What it is I should have thrown the tablet away. Is you're going to end up here with 12 bits of numbers, or sorry, 24 bits of numbers. The upper 8 is the ASCII code for H. The next 8 are the ASCII code for lowercase e. The next 8 are the ASCII code for lowercase l. You see that? That's what we end up with. And then to convert, to do the RSA encryption, you just do a POW-M, you call POW-M, passing in the message to the eth power modulus by n. And that's your S. That's it. That's all of RSA. And to decrypt it, you do a POW-M again. S to the dth power mod n. That's the whole assignment. Okay. And then you do, decrypting it. Modulus by 256. If you modulus this by 256, you get the bottom character. Then right shift it by 8 bits, modulus it by 256, get the next character. You will get all the characters out backwards. And so I will leave it as an exercise to the reader on how to reverse a string. Is there a standard library function to reverse a string? Yes, there is. So you can just make a new string and push back each character off of it. Do you guys understand why modulusing by 256 will give you the last character here? Lowercase l. Modulus 256 gives you the bottom 8 bits. And so you just pull that out into a character and call pushback, push it into a string. And you'll end up with hello world backwards. And then you can just call reverse. There is a standard library function to reverse it. Or if you want to be fancy, you could put it into a deck or a stack. You know, push all the characters into a stack and then pop them off, and they'll come out in the right order. If RSA is this predictable, what is it that makes it so secure? Because D is not shared with anyone. So this S here can be published on the world. I could go onto my website right now and put up a giant big old number that's my S, and nobody can decrypt it. Even if they know who I'm sending it to, if they know that I'm sending it to Glenn Greenwald, formerly of The Intercept, even though they know his public key, which is ENN, they can't decode it. They cannot figure out what M is based on S. So I sent him this big encrypted, something like poking me. I sent him this big encrypted email, and even though everybody knows, yeah, there's like a piece of plastic sticking out. There it is. Wow, look at that. Okay. Even though everybody knows his E, everybody knows his N, and they've intercepted my S, they still cannot get the message that I sent to him. That's the power of RSA. The only person who is able to decode it is the person that has the D, right? The D is the secret key, right? So Glenn Greenwald does the opposite transformation here. So he computes the message that I'm sending him by doing a POW-M, passing in the secret message to the dth power modulus n. One line of code to RSA encode, one line of code to RSA decode. That's it. It's one line. It's just POW-M. It's power modulus function. Don't do POW. Don't do POW and then do modulus. Use POW-M. This is a giant number. That's 65,000. If you take a giant number to the 65,000th power without using POW-M, if you just do POW, you're going to have a bad time. You will have a very, very bad time. Use POW-M. So remember how we talked about how fast that is and how easy it is to do. Is RSA still used? No, there's better algorithms, but the math still works, and it's easy enough to understand why it works that I teach it. And the reason why it works is because factoring is hard. This number here, n, is published, and all it is a product of two primes. If there was an easy way of going from a number to factoring it, RSA encryption wouldn't work. And so there's quantum computing, which maybe someday will make RSA pointless. So something called Shor's algorithm, which will allow you to factor. Look at that big O. Look at that big O time. It allows you to factor prime numbers in reasonable time. Order log n squared times log log n times log 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 n. Can you imagine doing the proof of that? My lord, I'll just give up. Oh no, that's the number of quantum gates you need. It's almost exponentially faster. So it runs in order e to the 1.9th power times log n to the 1/3 power times log log n to the 2/3 power. I could not even begin to imagine trying to write a proof of that. It's undoubtedly ridiculous. So, wait, no, this is a number sieve. No. Sorry, that is the number sieve running time. No, it's just log n. Okay, yeah. So basically, Shor's algorithm can factorize things in almost instantaneously. Yeah. The trouble is you have to have enough quantum gates, and right now we have like a dozen or so. Yeah. Basically, quantum computing might make it obsolete. And so, as a result of that, because we've known about this since the 90s, there's a movie called Sneakers, which was actually based on this algorithm, Shor's algorithm. It came out around the same time as Hackers. No. And so those were two great classics. Okay, it was a little bit earlier actually. Two great classics in Hacker movie. They're both terrible movies, but like they're fun terrible movies. So Robert Redford, yeah. Dan Aykroyd, yeah. Basically, the premise of Sneakers is that a academic has invented a Shor's algorithm and has actually built it. And so, using this box that he has, he can essentially factor prime numbers instantaneously and thus defeat cryptography. And so, what happens is that he immediately comes to the attention of like every, 3-letter agency in the world, the KGB, CIA, whatever. And I think he gets assassinated, and like they're sort of there's like this crime team that's trying to steal it and stuff like that. So it's a classic hacker movie. Okay. So, do we learn other cryptographic methods? Sure. I will teach you my favorite one right now. It's called Rot13. You take a letter and add 13 to it. So if you take the letter A, you get N. And it's symmetrical. Look, N becomes A because the English language has 26 letters in it. Doesn't work for other languages, unfortunately. So ABC becomes NOP, LMNOP, right? ABCD, NOPQ, yeah. If you type in NOPQ, ABCD, it's incredibly secure. And you can also use Rot13 to get your hacker name, of course. So Bill is, of course, OV. Kearney is X-Real. Doesn't seem very helpful. I didn't say it was a good one. Me and Crowley just want to know, are we going to learn other cryptographic methods? And there you go. It's easy to implement. Shahab becomes Funono. Then Corelli becomes Zarapinriv. That's a great hacker name, dude. Zarapriv. Dotstheimer becomes Libsgrivsgr. Krente becomes Pibirigar. Nate Beal has the best one. Nate Beal is, of course, Orny. Vargas is INET NF. That's actually a good name. INET is an abbreviation for the internet, right? So Vargas's hacker name is Internet NF. It's pretty good. Not found. Internet not found. That's a great hacker name, dude. It's an amazing hacker name. So, yeah, Joshua. Nah, just use your last name. Internet not found. It's a great name. Yeah. Lulz. Yeah. Aaron becomes the Nebba. Okay, so there you go. There's Rot13. It's unbreakable encryption unless somebody knows what you're doing, in which case it's very breakable. Obama, yeah. Yeah, it's highly secure. If you can't pronounce it, it's secure. Yeah. Okay, so yeah, so I think everything you need to know about RSA. I'm trying not to hold your hands too much on this because it is only about 12 lines of code total for this whole assignment. Something like that. Maybe if you want. I don't know. Yeah, so you compute E, N, T, and D, which is 4 lines of code. You need to use Miller-Robin. Miller-Robin is yes, sir. Yeah, go for it. Thanks, Discord. Okay, so there's the so basically you just started the number typed in. If they type in 100, it's even, so you go up to 101. And then you use Miller-Robin. Is 101 prime? If it is, there's your P. If not, you go on to 103. Is it prime? It is. Cool. There's your P. If not, you go on to 105. You just keep checking every odd number going up using Miller-Robin, and the documentation there has an example of how to do it. It's 1 line of code. You might need to make a random number generator, but that's in the example as well. Okay. So that's our thing. Can we get a break? Yes, it's 11 o'clock. Sounds good. So let's meet back here in 10 minutes, and we will move on from here. If you guys have any further questions about RSA, just post it on the chat channel, and I'll answer it after the break. Okay. I'll leave this up here for now, too, so you can admire it. We are back. We're back. All right. So... yeah, nothing I said here is anything new. All this is in the README file anyway for the assignment. Yep, and if you want to test your code, then you can do so by running input tester. Right. And if there's a difference, this is what you're outputting. This is what it's supposed to output. And when it works right, it should look like that. So this is what you get when all input tests are passed. 10 out of 10. And if you do the extra credit by getting the format lib to work properly with the CPPent class, I'll give you an extra point. Okay. So that's enough for the coding side, I think, for now. Let's talk more about RSA from a theoretical perspective, and maybe some attacks we can make on RSA. So Shor's algorithm is one of them. It's a log-in way of factoring numbers, which is much faster than the current way, which is exponential. Like I said, man, that big O time for the number sieve. Man, I would not want to be the person trying to figure that out for the first time. My lord. All right. So RSA encryption, hashes, cryptographic hashes, yeah. So you can cryptographically hash something to sort of verify that it is the thing that was hashed, if it's good, if it's a good hash. Okay. So how do we attack RSA? So the thing is, like, it's hard to attack using the assumptions that was used to make RSA, right? So the assumptions for RSA is that Bob's public key. The public key is just E, which is always 65537, and N, which is the product of two large primes. And so as long as the assumptions for RSA hold, namely that N is a large number, then there is no feasible way to factor it. We can make it easily by doing multiplication. Factoring those basically impossible. As long as that assumption holds and you don't make any obvious mistakes, RSA is basically pretty secure until at least quantum cryptography comes along, right? So different ways of attacking RSA. If N is small, then you can factor it, right? If I say my public key has an N of 15, you're like, all right, well, your primes are 3 and 5. Like, there you go. Done. I factored it. So as long as you have large prime numbers, that's basically impossible, practically impossible. If you have, like, if your random number generator isn't very good, and people that's why when I did the putty keygen, I had to move my mouse around as like an extra source of randomness. What if you generated your public keys based on the time, right? This is something that a lot of people do, right? They will initialize the random number generator using the current time. They'll do something like this, right? Then main.cc. In fact, we often teach people to do this, like srand time 0. So this initializes the random number generator with the current time, and then the seed that we're going to use for picking a random number would be like int rand, something like that, all right? So this is amazingly insecure. If you use this to generate a 500-digit random number, there are two glaring gaping holes in this system. So if we use this random number generator here and we plug it into some sort of like thing that will spit out our P and our Q, there's really, really serious problems with it. Can anyone find one of them? What was the holy crap for you, Oxtimer? It's pseudo-random. Yeah, it's not random, right? So it's pseudo-random. Okay. So what is the problem with it? It's int, not CPP int. Yeah, that's a big problem. There's only 32 bits in it. You can exhaustively try all 2 billion, 4 billion possible seeds, right? In fact, if this was the crypto system that people use to generate the primes, I would just generate all 4 billion possible outcomes, right? Make a P, make a Q for every single one of the 4 billion possibilities that are generated by rand. If we actually get 32 bits of randomness out of it. Does anyone know what the actual amount of randomness is guaranteed by rand? How many bits of randomness were guaranteed? Does anyone know? By the standard? Well, yeah, that's the other problem thing. We'll get to that in a second. How many bits, like, I'm reading 32 bits out of it, right? Are all 32 bits guaranteed to be random? The answer is 16 bits. So it's actually, not you, then 2 rand, and 3 rand. There we go. The rand function is a pseudo-random integer in the range from 0 to rand max. And rand max is guaranteed to be at least 16 bits, which is 65,000 possibilities, which is garbage. In reality, it's going to be 32 bits, okay? But if you rand max is assumed to be 32,000. So not even the full short, half a short, right? So 32,000 possible numbers. You could generate that pretty much instantaneously. You could generate every possible prime, all 32,000 primes or pairs of primes, and then you multiply the p's and q's together. You get the n's, and you see, oh look, he picked number 50. Okay, and so if he publishes an n based on this, we've generated all the different p's and q's. We just multiply them. We're like, oh yep, that matches. So I know what the factor is. So even if he has a 500-digit long number, I can still factor it because the system that he used to generate the random numbers, the long prime numbers, randomly was bad. This is why I say, like, if you want to make your own crypto system, don't. You know, it's there's so many different ways you can introduce a weakness into your code. And then the other thing Mr. Singh pointed out, which is that it's seeded based on the current time. And so if two people make a P and Q at the same time, they'll have the same N. And in fact, a lot of these keys actually have the day, at least, in the name. I don't know if it's more precise than that. But yeah, you could just run through all the seconds in the day and generate, try midnight plus 1 second, midnight plus 2 seconds, midnight plus 3 seconds, right? Just try every second in the day and generate a random P and Q from that, and then see if the P times Q matches the N that's published. Oh, there you go. It's factored. Do you guys understand? Do you see how we can factor N by just guessing the P and Q? Yeah. Try 503, try 504. Generate the P and the Q from it, multiply them. Does it match? No. Try 505. Multiply them. Does it match? Yes. Okay. We've factored it. Do you guys understand that? Like, you can factor things by, if you can generate the prime numbers randomly the same way, you don't need to actually factor them. You just multiply the two generated primes and see if it matches. Do you guys understand that concept? So don't use this for anything serious. If you're making an online casino, don't use RAND, don't use SRAND. 100% guaranteed, do not use it. It's easier to write code, it's a lot more compact to write code using this. For any serious purpose, you're going to want to include random, which has much better random number generators, and they can just generate a bunch of bits of randomness for you. So you can have it generate 500 bits of random zeros and ones, and then start from there and hunt for primes. And the random number generator can tie into the system source of randomness and entropy, we call it, and do a pretty good job generating random numbers. Okay. Bigger and more random P and Q, less likely to be cracked. Much less likely to be cracked. Yeah, if you can generate your P and your Q actually randomly, that people can't predict, then RSA is pretty good. Yeah, until quantum computing comes around, which is why people have been moving away from systems that you can break with quantum computing. That's why when you're asking, like, do people still use it? Yeah, but also no. Okay, so the third bullet point takes place when your D is small. Okay, so if you have a small d, and that means about a third of n to the 1/4 power, then there is a mathematical attack that I don't really understand called Wiener's attack, and basically it only takes place if you have a small d, and so all you have to do is just, when you generate your d, just make sure that it is not below the mathematical threshold, and it's just a simple if statement to avoid this. Okay, so you can. That's what you're looking for there. So as long as the d is smaller than a third of the fourth root of n is the big multiplied prime, then you're vulnerable. Okay. So And so it goes into the attack here, but yeah, all you have to know is small d, Wiener's attack. Okay. You guys understand? I mean, you don't have to understand the theory. Just you understand this bullet point here. Okay. Okay. So one of the nice things about crypto is you don't actually have to understand the proof necessarily. You just, like, if you're writing the code yourself, you can just be like, all right, you know, take the fourth root of it, multiply by a third, check d to see if it's, you know, see if the d is big enough. If it's not, start over. Okay. All right. What if your message is really small? Like, what if you're sending the message of 1? Do you remember how RSA cryptography works? You take the message to the eth power, modulus it by n. So 1 to the eth power is always going to be 1. And so the answer, so people could decrypt it, right? So if you're just sending 0 or 1, 0 to any power is 0, and 1 to any power is 1. And so if, like, the only 2 messages you ever send using your RSA crypto system are yes and no, you're like, oh, I'll just send 1, or I'll send 0. Guess what? You're not encrypting anything, right? And anybody can decrypt it. And so you have to make sure that m to the eth power is bigger than n. So there's at least one modulus going on. If you don't ever do a modulus, then people can, right, because you just did m to the eth power. If there's no modulus, then people can decrypt it by just taking the eth root. You understand? Like, if let's say n is like really, really, really big, right? Like super big, which it can be, because these are oftentimes very big numbers. So if you take m to the eth power and it's so big you never do a modulus, like m to the th power is small, and that's one of the reasons why e is often 65,537, because that will oftentimes push it past n. If you have an e of like 3 and n is like 1,000 digits, then yeah, this can actually happen, right? So if this is actually smaller than n, then there's no modulus. And so if you want to, the secret message is m to the eth power in that case. And so to recover m, you can just take the not 3, the eth root of the secret message. Right? It's just algebra. So if you never do a modulus, then you can just use math, and one answer gives you the result. So these are just these are not serious concerns, like I said, because these are very small things that we can check for. Like, make sure P and Q are big, make sure N is big, make sure your D is big, make sure m to the eth power is going to be bigger than n. Like, these are all very simple checks you can put in, but there's still things that you need to do, because if you don't, horrible things will happen, right? You'll get the hacks. So, yeah, don't send 0 or 1 as a message, because you cannot encrypt those things. You have to use padding to do that. Okay. This next bullet point here is actually a much more practical attack. These attacks here, you're only gonna hit them if the person who made the crypto system has no experience making them whatsoever. And maybe that happens, right? Like, a lot of people just try to roll their own implementation, and they use like Rand or something. There is a chance, that when people roll their own, that they made some fundamental mistake. Which is why I say don't try to roll your own crypto system for realsies. It's fine for a classroom assignment, but don't do it for realsies. So let's talk about rainbow tables. Did I close OneNote? I must have. Okay. So this is actually a practical attack. All right, so we got Glenn Greenwald, formerly of the Intercept, over here. He's sitting over in the UK somewhere, United Kingdom. He's across the pond. Here's England over here, Ireland, America over here, right? And we're going to send a message to him over the web. So he has published his E and his N. Okay. So if we have a message like, you know, Snowden is in Russia or whatever, we convert this string to a number by doing the bit shift trick. And then this is our message, right? And so we compute S, the secret message, we're going to send over the wire. We're going to say S is equal to pow M message to the ETH power modulus N. And we send this over the web. So let's say that one of the 3-letter agencies intercepts this message. This is public, right? E to the nth power, or ENN, sorry, is public. S has been intercepted. And so you might be like, well, nobody can read it, right? It's the only person who can read this is Glenn Greenwald. And assuming that the crypto systems have been made properly, that's true. But what if you can guess the message, right? What if you guess, you know, Snowden is not in Russia? What you do is you try, you know, some new message. Let's call it message 1. And that's like Snowden is not in Russia. What you can do is you can just take this letter and do the pow m to the e mod n, and see if the S you get matches that one. Nope. Okay, that's not what they sent. Try another one. Snowden is in Russia. It matches. Okay, so we know what message was sent now, right? So this is one of the this is one of those things where, like, you have to use padding and things like that to add extra random characters to your messages, because if you send a message that somebody can guess, like, you know, attack at dawn or something like that, attack at night, people trying to guess people trying to break your encryption will just guess different emails. You know, attack at dawn, attack at night, attack in the morning, attack at 10. And they'll try thousands and thousands and millions of possible messages that are the most, they'll do like a statistical analysis of messages, figure out what the most common messages are, and they will try each one of those messages, M1, M2, M3, M4, they'll try all of those messages, M999,999 to the ETH power mod n. We got a match. The secret message created by that is the same as the secret message sent over the wire. We now know that the answer is we're going to have a snowball fight in Moscow or something. Okay? That's a lot of brute force. It's a lot less brute force, though, than factoring. Right? And so this is how password cracking works. So what you do with a password cracking, it's not RSA, but there's a cryptographic hash, right? So when you log in on the server, there's a function called crypt. I believe it's been a while since I've looked at this. Yeah, and so you pass in a string, and it gives you an encoded string. And so when you log in, it shows the when you log in, you type in a password. It calls crypt on it, and then it checks. It's a cryptographic hash, basically. And it checks the hash stored on the system with the hash of what you just typed in. If they match, the same password was made for it. Congratulations, you're logged in. And so the way that we crack passwords is we guess. So we try password as your password. We run it through crypt, see if it matches. If it does, your password was password. We're going to try password 123. Password 123 exclamation mark. Password 321. 1234. 12345. 123456. And so every semester I run a password cracker on students' passwords. I run it both on the server and on my machine here that has a fairly beefy GPU. It guesses 256,000 passwords a second. So I let it run for hours. And what we have on here is, let's see, can I find where I put it? I don't know where I put it. I have a dictionary file on here somewhere. I don't know where it is. But there's a dictionary file that contains all the most common passwords and all the English words. And so these password crackers will try combining them in different ways and adding numbers and reversing them and adding an exclamation mark and a hyphen and things like that. If it'll run through all the top most common passwords. So 1 2 3 4 5 6, 1 2 3 4 5 6 7 8 9. How secure is that? QWERTY, password, I love you, nothing, secret, password 1, admin. QWERTY UIOP 18. What is this? 18 ATC SKD 2W. Yeah. So if your password is dragon or football, change it. Okay. 1 2 3 QWE. No. Change it. And so password crackers will run through all these. And I let it run for hours. So it tried. How many passwords is that? So if I ran it for, let's see, it does about 250,000 cracks per second. So 15 million a minute, 900 million an hour. I ran it for, let's say, 4 hours. So that's 3.6 billion passwords that I tried. So it starts with the most common and it works its way down. All right. Try to guess yours. I don't know. Sing 1 2 3. Yeah, and then all the students whose passwords, I guess, which was about 13 this year. So 13 students' passwords out of the 90, 40, 100 something, students. So I got about 10% of all the students' passwords. Yeah, doing that. Okay. Yeah, and so what you do, if you really want to be cool, is you just save all of them. A dictionary attack is where you just go through the dictionary and you just keep encrypting them and see if they match. If the encryption matches, then you've decrypted it. And then there's a rainbow table attack where you save them all. So rather than running through all 4 billion things that I did over those hours, I just save them all to a file and put them into a hash table. And then I don't have to do any computational anything anymore. What I do is I just run through all of your encrypted passwords and see if any of them match. If they match, hash table lookup, order 1. Your password is password 1 2 3. That's it. You don't even have to. You just need hard drive space, which is cheap, right? And so if you save the most popular trillion passwords, you're probably going to hit a good solid 15-20% of the time, maybe, depending on how lazy people are and how strict the password requirements are on a system. With no computational effort whatsoever, you're just going to pick up 15% of all people's passwords if you can acquire the password file. So that's called a rainbow table. All right. Imagine the odds on high traffic sites. Yeah, if you were able to acquire the password file for Google or whatever, then you can do an offline attack, which is what this is called. An online attack is you just try logging in as somebody on Gmail, right? So I'm going to try logging in as Min Corelli, and I'm going to type in password 1 2 3. Password failed. And so an online attack, I can sit there guessing passwords over and over again. And that's why well-designed online systems will lock you out, or they will slow down. They will iteratively slow down the more you try to log in. Because if you lock people out, that's a denial of service attack. I could prevent Min Corelli from ever logging in on Gmail by always trying to log in as him, and it would keep locking the account over and over again, and nobody could get in, including him, right? And so what they typically do is they'll progressively slow down. So you type in a bad password, and if it waits like 4 or 5 seconds, that's because they're doing a progressive slowdown. And if you do that, then online attacks become infeasible. Maybe you can guess, I don't know, some, but the rate that you can try passwords, rather than 250,000 a second, you're doing 1 every 5 seconds, right? So you might get lucky if somebody has a really terrible password. And then also Gmail could detect somebody is guessing passwords. They tried password A, B, C, D, E, F, G. And they're like, all right, somebody's trying to crack this guy's password. Maybe they notify you, hey, by the way, somebody's trying to come after you. Make sure you change your password to something hard. Okay. So that's an online attack. An offline attack is when you have a copy of everybody's password hashes, and you can sit there and throw computational power at it, trying to guess them. We rarely brute force. Like, we never go A, B, C, D, E, F, G. You know, we don't go down the line. You can, I guess. And that's feasible for small passwords. Basically, any password smaller than like 12 characters, they've probably already computed a rainbow table for it. So any password smaller than 12 characters, don't expect it to be secure at all for an offline attack. They will probably get your password instantaneously because they can just pre-compute all of them. Okay. So one pet peeve of mine is that they make passwords too difficult, right, to remember. Like, they'll say you have to have 12 characters, one special character, one number, one uppercase, and things like that. And that requirement's only needed if somebody's going to have an offline attack. For an online attack, it does not need to be that secure. There's a great article in the ACM on this issue where there's really two different threat models. The first is people trying to brute force your password by guessing it online, and the other is they've acquired your password file. And these threat models are very different. If you're worried about a government level actor like the NSA, who have these giant data centers, and they want to throw every bit of computational power at you, any password shorter than, like, I don't know, like 20 characters, like, you should not be confident that they will not be able to break it. On the other hand, people just randomly trying to log in as you actually don't need that strong a password. Throw a password cracker at everyone's passwords for a couple hours, and if you do that, you've already guessed, like, what was it, 1 billion passwords. An online attack where they can guess once every couple seconds is not going to get it. So the recommendation of the ACM, or the author in that ACM article, was to actually make passwords on websites easier and less secure, which is a weird concept, right? Because simply online attacks that can guess once every 5 seconds aren't fast enough to be able to guess your password. Okay? And when they can't remember their passwords, they tend to make them insecure. Okay, I need 11 letters. Okay, it's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right? So the recommendation was that all this security theater, like you need a special character and a number and all that stuff, is ineffective or wastefully effective for preventing online attacks, and don't help at all against offline attacks. And so they're pointless. A friend of mine used to work at a company called College Club. College Club recruited a lot of computer science majors. They were freshmen and sophomores. They would pay them minimum wage. They would promise them stock options that, of course, would never materialize. It was really a pretty exploitative company, but a lot of tech, my friends in tech worked for them because it was work experience and because they bought into the cult that they were all going to be millionaires someday and all this kind of stuff. College Club was like a discount club for college students, but they also had a voicemail system, and they had an email system, and you could have your own web page, and so it's kind of like this all-in-one place where, like, they wanted every college student to come to. This is before Facebook, obviously, and like a social network essentially, but it just never took off like Facebook did. So yeah, and all, yeah, if people reuse their passwords, all you need is one bad website to be compromised, and then your password, if you reuse it on a different site, is now compromised as well. That's in fact how my World of Warcraft account got compromised. I used the same password on World of Warcraft as I did on this website that got compromised, and so hackers logged in as me on World of Warcraft and deleted all of my gear, and left me stranded in the wilderness, naked, floating in a river, drowning to death. You know, so yeah. So don't reuse your passwords. It's a bad idea. Firefox has the ability to randomly generate passwords every time you make a new account. Of course, the randomly generated passwords don't meet the password safety requirements, which is ridiculous because these passwords they generate are like 24 characters long, which is usually pretty good. But because it doesn't have an uppercase or an exclamation mark in it, it's like, oh Lord, you know, so terrible. So yeah, so so College Club, like, I considered it like a cult, basically. Unpaid overtime, minimum wage, selling these gullible freshmen and sophomore computer science students these pie-in-the-sky dreams of becoming millionaires that would never materialize. The guy that ran the company ended up opening up mp3.com, which, of course, got shut down due to them pirating everyone's music, which I'm not sure how he thought that was going to work out, but it didn't. So have I been pwn.com? Yeah, that's good. Yeah, so anyhow, so the point is that I was sort of annoyed at the company, a little bit, because I saw their sort of exploitative practices, and my buddy worked there, and so I was able to what you might call hack the company, and I did so by getting a list of all the users that were logged in on their Unix server, because they allowed that. You could poke it with a finger request is what it's called, and it would send over the internet the usernames of everybody logged in. I'm like, cool, thank you. And so it would, I'm like, finger, at collegeclub.com, bloop, here's the list of everyone logged in, cool. So I wrote a shell script that would do that every, minute or so, and add any new names to a database. And so I compiled over the span of a couple days, all the active users on the system. I then did an online attack where I would log in as people and try guessing passwords and things like that. And on the third login, I was able to get in. It was their voicemail account. It was the account for their the account that was used to set up their voicemail system. Like, you would call in and you would get your voicemail, and they had a whole thing. Like, you get movie times on it. Like, it was a really complicated system. And so the voicemail, which wasn't a real person, had a very limited Unix shell. And did I get my gear back after the hack? Yeah. Customer service restored my account, and they said you have to install an authenticator, a Blizzard authenticator, to go forward. So because it wasn't supposed to be an account that people used on Unix, it had what's called a restricted shell on it. So when you log in on a Unix system, let me know if I'm boring you guys, but I don't know. It's kind of a useful story when it comes to cryptography. I think the statute of limitations is expired. Not CD, them, SC password. So if you look at all the accounts on here, you see that these guys have their shell set to be no login. So what happens is that when you connect to a server, if you provide a correct password, it runs whatever shell is in yellow there, right? And so like like Tinoco, it'll run TC shell, right? And so and I just put up everyone's username so feasibly people could try an online attack. But like I said, I've done the offline attack, and so I'm not worried about an online attack because I've tried over 1 billion passwords on these guys. So so the point is that when you have a system account that you don't want people to log in remotely from the internet, you just set the shell to be no login. And when you do that, it just logs you off immediately. It doesn't allow you to log in, essentially. They did not set it to no login. They set it to a restricted shell. A restricted shell being one that has very limited functionality. Like, it only allowed 5 or 6 commands. It had, I think it had email set up. And I think that's why they had it set up, because like when an error occurred, it would put an email into the email directory and be like, system went down for 5 minutes, blah, 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 blah. And so you could log in as this voicemail, username, voicemail, password, voicemail. You could log in as it and then check through the email and see what the thing is, but you couldn't actually do anything with it. So I think they weren't too concerned about people remotely, like me, logging in, because at worst you just read when the voicemail went down. Something like that. So how did I get out of the restricted shell that only, like, it's not even like a Unix prompt like this, right? Like when you log in, it's literally, it looks like this. Like there's just like 5 options you can do. One was email, one was, I don't know, check the current time or something. Yeah, there's just like very limited options as to what you can do. And so what I did was I went into the email client and I went into compose message like that. I'm like, okay. So I could send an email to my friend, and I did like, hey dude, how you doing? And he saw it and he just deleted it. It's like, And one of my friends is logged in as a voicemail and is being a goofball and emailing me. So, just kind of poked around a little bit, and I saw that there was an option. Cancel message. Yes. There's an option for config. Config. Somewhere within here, there was an option where you can set the editor that you use for the mail, right? And so I set the editor to be Vim, or VI it probably was back then. Okay, and you're like, all right, how does that help? You know, other than the fact that you can now use the power of Vim inside of email. Well. As it turns out, commit changes. No, I do not want to commit changes. As it turns out that in Vim, if you type : it gives you a Unix shell. So I ran that, and of course the Unix shell that it ran was the restricted one, so I was right back where I was before. So what I did instead was I said run the Unix command /bin/ csh or whatever it was, and boom, I have a unrestricted shell that I can then use. So then the first thing I did was vim etc password, and I copied everyone's usernames and their password hashes because they did not have a shadow password file set up. Instead, it had everyone's cryptographically encrypted passwords right here in the document. And so I copied them over to the supercomputer that I had access to, and I ran a password cracker on it for a couple days using the power of a supercomputer to do so. And got 130 passwords out of a company of like 400, 500 people, something like that. They were all paying minimum wage and exploiting. I got about 100 of them. I don't know. Maybe not quite 100. Some, order of magnitude somewhere around there. It was a long time ago. But so what I did was I got all the usernames and all their cracked passwords, and I drove to Campus Club, and I walked around the office. I'm like, oh, Mr. Smith, do you like cinnamon girls? Huh? What are you talking about? Who are you? Cinnamon Girl 123. Just ring any bells with you? What? How do you know my password? All right. Have a nice day, Mr. Smith. Mr. Jones, you like surfing, huh? Surfing USA 123. Ring any bells? Well, I'm gonna change your password, buddy. And I walked around the office and I told all the people that their passwords were invulnerable, or were not invulnerable. Their passwords were vulnerable. And, I didn't do anything with it. I didn't mess with the company or anything like that. I just walked around the office telling people what their passwords were. And promptly got banned from the facility because the owner of the company decided that I was a spy for the Chinese government, of all things. The Chinese government. Not the U.S. government, not the Russian government, the Chinese government. And he was absolutely convinced that I was a spy for the Chinese government because spies, once they hack your company, they walk around and tell you to change your passwords because they're insecure. Because that's what spies do. They're just helpful individuals who will notify you when they've compromised your system and very helpfully tell everybody with a bad password to change it. Because that's exactly how reality works. Dude is delusional. So that was... should have increased the wages of the workers from the shell. No, it's not like I did anything horrible with the company. It was just mostly just an exercise, in security, and my friend was I think I was invited by him to try and test the security of the system, so I don't even think it was illegal per se, but he was confident the system was very secure. And then I ran through all the different reasons. You need to get a shadow password set up. You need to not allow Finger to work so that I can get a list of everybody on your system. You should probably not allow remote connecting to your server unless you whitelist the IP addresses. I went down a list of things that needed to be fixed for them. And not like I got paid at all. I just did it because it was amusing to me. And then I got banned from the company for being an agent of the Chinese government. I had not even studied Mandarin yet. Can you believe that? It's ridiculous. So imagine being banned for being helpful. Yeah, but that's the reality of the situation is that companies are oftentimes very stupid when it comes to security. They don't invest into security until it bites them in the ass. And when it bites them in the ass, then they flail about and look for excuses and things like that. There was a hack, a year or two ago of the credit union, right? That was a gigantic hack. Target was found storing people's usernames and passwords and credit card numbers in plain text, which you are absolutely not supposed to do, ever. Like, if you run any sort of e-commerce site, you will have gone through this. You are not supposed to store people's credit cards in plain text. You know what I mean by plain text? Like you have a file called, like, credit cards, and it's like Kanoko, 543, 343, like having the actual, like, you're not ever, like, even if you save your credit card on their website, it is not supposed to actually save your credit card number. You don't need to do that. There's a system set up. You save the cryptographic hash of the credit card, more or less, right? You do not actually save the credit card number, because if anybody compromises the website, like what happened with Target, then thieves get everyone's usernames and socials and addresses and credit card numbers, and they can use that to commit mass identity fraud, right? Mass identity fraud. You were not supposed to do it. And Target, one of the world's largest retailers, yeah, and like, Visa, like, audits people on this kind of stuff, right? Like, they actually, like, a friend of mine does that. He travels around the country, and he's like, log me in on your Unix system, and he goes through their source code, and he goes through all their data files and things like that, verifying that you do not store a credit card in plain text anywhere on the system. So what happens is, like, if you click, like, save my credit card, like you buy something off, like, Amazon or something, you click save my credit card. What happens is that, you type in your credit card number once, and you type in the 1234, like the little 4-digit thing on the back of the card. And what happens is that goes to Visa, and then Visa hands the retailer a token. And that token can only be used by that retailer. So even if that token gets stolen and somebody else tries to use it, it doesn't work. That token says Bill Kearney on Amazon is credit card, Amex 11110011, And so every time I say, use my saved credit card, then it sends the token over to Visa, and they authenticate, right? And there's sometimes additional authentication steps. They can save the last 4 digits, I think, in plain text, so you know which card it is. But you are not supposed to have the card anywhere in plain text. And that's what my buddy does. He travels the country. Log in on the mainframes. He's like, log me in, dude. And he spends 2 or 3 days going through your code, looking for that that mess up. Yeah. Iowa paid coal fire to penetrate test courthouse, then arrested them. Yeah, and that's what I'm saying. Like, Sony, right? Like Sony, was it like the GeoHot guy? What's the guy's name? George Hotz. Yeah, Sony's war with GeoHot. So that there's a whole story involving that. He jailbroke the PS3. They tried suing him. Sony got a class action lawsuit for turning off Linux support. So I actually had one of the original PS3s. It could run Yellow Dog Linux on it. And so Sony patched the PS3 to not be able to run Linux anymore. And so I got actually a payment from the class action lawsuit. I got like $2 or something because they broke my PS3. So they sued him, and then there's this whole saga that you can. I'll just post it onto Discord with this stuff. Yeah, but my point is that the way that corporate management reacts to security is usually there's there's two different modes. The first is before they get hacked, they treat it like it's not an issue. Like, they just don't invest any money in it. They don't hire security people. They don't take it seriously. Nortel, which used to be one of the world's largest telecom companies, as described in the book Cyber Spies by Correa, didn't have any real internet security. And even after their IT guys were like, we're getting hacked left and right, and they're stealing our intellectual property, the C-level people kept it quiet because they didn't want it to tank the stock. And they're like, do nothing. So what happened was all of their intellectual property and trade secrets were stolen by China. And Chinese competitors came out with all their stuff at a cheaper price, and Nortel went out of business. So that's one option, is just to ignore it. The other option is after a disaster occurs, then they go into blame everybody but myself mode, and they sue, George Hotz, and they flail about, and they blame everybody except for themselves for ignoring security for so long. And those are basically the two modes, right? Ignore it, or after an incident, just just sue the world, and pretend that you care about security now. So one of the really interesting things to me is just how bad corporate America is at tech, even large tech companies, on a lot of different levels. The amount of stupidity in I was reading something about the fact that the people who make Windows at this point don't actually know how Windows works. I don't know if that's true or not, but it was a post by somebody who claimed to be working at Microsoft who's like, yeah, we don't know, the source code's too big, we actually don't know, we don't have a complete view of Microsoft Windows, we focus on little tiny parts to work on. I don't know if it's true or not. Bug bounty thing, or another famous story would be Steam hacker arrested. So if you remember the source code being leaked for, was it Half-Life 2? Is this not the one? Maybe this is a different guy. Yeah. This is amazing. So this guy hacked into Valve and found the source code to Half-Life 2 and posted it online because he was a big Valve fan. And he was curious how far along in development Half-Life 2 was, and found that it was not as far along as people were hoping it was. And because the Half-Life 2 source code was posted, people would be able to make hacks, and so it delayed Half-Life 2 by quite a while as they had to retool how their client-server model worked to avoid being hacked because their protocol was visible, which means it probably wasn't that secure to begin with. And so what happened was Valve sent a job offer to the hacker. And then the guy accepted the job offer and he got arrested. So, I think they arrested him in Europe. The whole thing was, they wanted to bring him to America and arrest the hacker here. But he got arrested in Germany, I think, before he could go to America. And the German police were like, you're lucky that we're arresting you and not America. Valve manager staged a 40-minute job interview with the hacker over the phone. He confirmed his name. He talked about how he cracked the network. He sent them his resume. And what's really funny is that this actually does happen sometimes, right? Corporations do actually sometimes hire people that hack them to fix their security. And so this guy thought that Valve, they're a legit company. They're not gonna pull a tricksy on me. And nope. They were out for blood after having to delay Half-Life 2 because of this guy. So, isn't that entrapment? I mean, my best friend used to work for ArenaNet on Guild Wars 2, and one of his coworkers, a nice Swedish fellow, hacked in and finally fixed their code, and that's how he got hired. Yeah, it does happen. It does happen. And in fact, there's some rather amusing stories of like router vulnerabilities getting patched by hackers. So like somebody will hack into a network and be like, through the router vulnerability, and then they patch it so that other hackers can't get in the same way. And perhaps I shouldn't be using the word hacker. My boy Richard Stallman doesn't like calling them hackers, because hackers are people with technical merit who like hacking around on systems and exploring and stuff like that. He likes calling them crackers, which is a term that just sounds like utterly ridiculous to me. The cracker. Sorry, you need to get a better term. If you want people to not use hacker, which is a cool term, you got to come up with a better term than cracker. I'm sorry, So, yeah, and there have been lots of hacks of like cryptocurrency and things like that, like and fraud too. Lots of fraud. Okay, so yeah, the whole security world is actually kind of interesting, and so I was originally interested in doing that as my specialization, and then I discovered how much math there was, and I sort of backed out of it after. I did all right. Like I took everything that was available as an undergraduate, but wasn't the same kind of thing that I thought it would be. So anyway, so what you can do to avoid these kinds of attacks, like with a small m, is you can pad it. So what you do is you say, we're going to attack at dawn, and then you add 500 random ones and zeros to it at the end. And then they're not going to be able to use a rainbow table to attack it, and it will also avoid this problem of having a small m. There's also other ways of bypassing RSA. For example, you take the person and hit them with a hammer. That's a perfectly effective way of bypassing RSA as well. You haul them into a room and hit them a bunch of times until they tell you the password. Another way you can do it is if you compromise somebody's computer, you can get the private keys off of it. If anybody has physical access to my computer here, they could copy my PuTTY private key files. If anybody was able to get in through my network, they could also copy the files remotely, and then all of my communications on PuTTY would be visible, right? Not like I'm not streaming it constantly anyway. My life is an open book. Yeah, security world's wild though. Like there's this one group that had the biggest bank heist, and it was foiled by a typo. The hackers managed to get a wire, $1 billion bank heist. $1 billion. That's a lot of money. So they didn't spell the name of the bank right. So they misspelled foundation as foundation, and they're like, let's call these guys up and make sure we're spelling it. They're like, what transfer? For anybody who says English classes are not important for computer science students, which I had a student tell me once, like, you can't make me write an essay. This is not an English class. Just remember, $1 billion hack was foiled because the hackers couldn't spell the word foundation properly. So, there you go. Study English, everyone. Okay, so, yeah, it's a true story. Yeah, like it's a wild world out there, and with all the cryptocurrency and that's just opened up all sorts of new ways of stealing money. All right, hashing. Yeah, and another way you can attack RSA is like when they broke into the office of the company that makes the private keys for cell phones. You just compromise that one point of failure, and then you get everybody's private keys. That's another way you can do it. So there's a lot of different ways you can come after people. Let's say that somebody took down my website and put up another website. Okay. And so my public key that I had up before isn't there anymore, right? So there's a new one. And then people will email me using the new public key, and it goes to, the NSA or something, right? And so that's another issue, right? Like if they take you down, you take down your website, throw you in jail, put up a fake website, they can sit there and sniff all of your correspondence, even if they don't get your original private key. People will be like, oh, here's his public key, and send you a message, and they can intercept it now. It's kind of like when they arrest a drug dealer and they take his beeper. A friend a friend of mine, his buddy did that and just sat there and answered the beeper calls for all the drug deals and arrested 200 people or something like that. Like it was LAPD's like single biggest day of busting people for drugs or something. He just did it by taking the drug dealer's beeper and then just answering every call. Yeah, sure, come over to the warehouse. If you take down my server and you put up another server on ccipherx.com, what will happen when you try connecting to it with PuTTY is like the server's signature has changed. So if it ever says that, what it probably means is I reformatted the server. That's probably what it means. But it could be somebody has put up a fake server, right? If they, there's all, like the internet's domain name system is inherently insecure. And I realized that back in college, just how insecure it is. So I could redirect apple.com to point at my own website, right? Back in the day, it's better now. Back in the day, I realized like all these domain names could be easily hijacked, like super easy. And I never did it because like I'm not a jerk, you know. But I was like, you know. And so there's something like 40 different domain name hijackings a day on the internet, a day. People's there's an attack on the domain name system, and somebody gets a domain name they're not supposed to have. And so let's say somebody hijacks ccipherx.com and puts up a new Unix server, and you try logging in on it, and you type in your username, you type in your password. Congratulations, you have now given your username and password to your opponent, who can then use that username and password to log in on my account. Or, even better, they log you in, you know, it accepts the password, and it gives you a Unix shell, but it says, oh, you have to change your password now. And so you have to type in both your current password and a new password. And then you save that and use it to log in on the real server. And then they take it down after a couple hours. I'm none the wiser, but they've compromised everybody's passwords in the meantime. That's one of the reasons why I use a private key to log in rather than a username and password. It's actually more secure. As long as my private key is safe here on my computer, then there's no risk of me getting fooled into typing my username and password onto a hostile website. I did that once when I needed a root password at a place that I was working. So I just had my boss log in and it sniffed the username and password. So if I ever need to install something, I had the root password. I think, again, statute of limitations is expired on that. So. Yeah, like anytime you type in a name and a password, there's a possibility somebody's going to intercept it. Even if you're at your own computer, even if you're logging on a trusted website. How do you know your Wi-Fi that you're connected to is the real Wi-Fi? How do you know? How do you know? How do you know, I'm connected to, Arasaka, Wi-Fi. How do I know that that's actually my ASUS router over there and not somebody parked in a car outside of my house with the same SSID? How do you know? Somebody pulls up in a van with network gear and they create an SSID with the same name as mine, and they boost the signal strength so that my cell phone preferentially chooses to connect to the one with a better signal strength than my router up here, which won't work probably if I'm in the same room, but if I'm in a different room, my phone's like, oh, I know Arasaka, and it connects to it because it's a better signal strength, and it routes all of my traffic through them. Pull up to an office in a taco truck, people come out to buy the tacos. It happens all the time, right? People love it when a taco truck comes into your office's parking lot every Tuesday, Taco Tuesdays. You just put a signal booster on a Wi-Fi signal there with the same name as the company's Wi-Fi. People will connect to you, and you sniff all their traffic, modify their traffic. Right? Can you check the IP address of the Wi-Fi? Can you? You mean like the MAC address, the hardware address? Those could be impersonated. You can essentially clone somebody's Wi-Fi router? You know, how do you, is your company looking for spoofed Wi-Fi nodes actively? Is that, are they even aware of that as a threat? You know, are they constantly monitoring the airspace around the company to see if hostile Wi-Fi nodes are popping up? Probably not. You know, so how do you know? How do you know? Don't trust anything on Wi-Fi. You know, tunnel everything, like have everything go through SSH or HTTPS. Then it doesn't matter if they're intercepting your traffic. But when you make a DNS request, that's in the clear, and they can intercept the DNS request and return a wrong IP address. And so when you're connected through the taco truck, the hacker taco truck, and you try going to Google, instead it goes to a website that looks a lot like Google, but isn't Google. Right? And so you need a trust network on there. You have to use HTTPS, which will verify the key given by Google through the trust network that it has installed on the phone to be like, that's not a secure, that's a hacker site. You know? So, but if it's a website you've never been to before, you know, they just say, oh yeah, we don't accept HTTPS. We only accept HTTP. That's what they do. Sorry, HTTPS is not allowed. And your browser by default will fall back into HTTP, not HTTPS. HTTPS is a secured, you can think of it as RSA, it's not RSA. But you can think of it as a secured RSA connection between you and Google. If you connect to Gmail, it'll say HTTPS gmail.com. But if a website says no, HTTPS not allowed, most browsers will fall back to HTTP by default, which is unsecured. It sends everything in plain text, and anybody who has a hostile Wi-Fi point that you're routing through will read everything in clear text. All your emails, if your username and password are typed in, that's in clear text, and they have a copy of it now. So there's add-ons you can install like HTTPS Everywhere that will, you know, and you can make it refuse connections on HTTP, but by default, it doesn't work that way. And so it's just inherently insecure. So a lot of SCCD things are still HTTP. Yeah, they are. And so what can you do? It's inherently insecure. Yeah. So be looking for inconsistencies in what you're looking at? Sure. Or you know, the hacker, after you log in, it'll just sit there and do the spinny wheel thing, like loading email, and you're like, ah, damn, you know, this website's so slow right now, and it just never loads. Or it puts up a message down for maintenance, check again in 10 minutes, you know. Or let's say you're at your company, you're about to log in and your username and password, and a friend of yours comes by. The friend's actually a hacker. You don't know this. They got a job at the company specifically to hack it. You're there in the office. Friend comes by. Hey, Min Curley, how you doing, man? Following the game, watching the big game on Friday. They got their cell phone there. And they leave their cell phone on your desk behind the monitor where you don't see it. Maybe they come back in 15, 20 minutes. Oh, damn, that's where it is. Oh, sorry about that, man. That's where I left it. I've been looking all over for it. You don't think anything of it. Kind of thing happens all the time. So, in the meantime, you logged in on your favorite website with your username and password. And now he has a copy of it. How? Well, every key on your keyboard makes a different sound. Slightly. So there's something called acoustic hacking. The cell phone can have its microphone on, and it can listen to the sound of your keystrokes. And over time, it'll build up a model of what each of the different keys on your keyboard sounds like based on the relative frequency of the keys that you type. And then when you log in with the username and password, it will be like HELLO321. Got it. Thank you very much. And so if somebody just leaves a cell phone, even if they're not, you know, connected to Wi-Fi or anything, or they're not even hacking your computer, just by listening to the sounds of your keyboard, they can get your username and password. There's also Tempest, where you can read the electromagnetic radiation coming off the computer and figure out what's being typed, how the mouse is moving. CRTs were especially vulnerable to that. That's where the term Tempest comes from. So in order for a... no, not Shakespeare. DoD requirement. So in order for electronics to be usable in a Defense Department building, they have to be Tempest certified, which means that you can't read the electromagnetic radiation beyond a certain radius. No freaking way. What? Yeah. Certified Tempest manufacturer program, test services. What is the radius? I think it's like 20 meters or 20 feet, something like that. So yeah, if you want to use a monitor, you have to use a Tempest certified monitor if you're in a secure zone. Otherwise, the electromagnetic radiation coming off of your monitor can be read and deciphered. Like with a CRT, you know how a CRT works. It's an electron gun, like an old school TV. And so what happens is it shoots electrons, and there's a magnet, and the magnet bends the electrons. And so as it bends the electrons, that magnet sends out an electromagnetic signal. You can actually view somebody's TV from across a parking lot. So, yeah. Let's see if I can find what the radius is. It doesn't really matter. I'm just kind of curious at this point. Tempest. Electromagnetic radiation. NSA methods for spy on computer emissions is classified. Yeah, okay, cool. Much of Tempest is about leaking electromagnetic emanations. Where is the shielding standards? Boom, 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 boom. Strictest standard. It assumed that an attacker has almost immediate access in a neighboring room, 3-foot distance. Then there's a relaxed one that's 20 meters. And then there's more relaxed, which is 100 meters. And so what they do is when you have a top secret facility, it's usually in a separate building, and there's a giant void space around it. And part of the reason for that is for Tempest requirements. So if you're leaking electromagnetic radiation, if somebody's sitting there with a laptop and a giant antenna, like, they'll be right there and you'll see them, right? Like they will have a clear zone with barbed wire and a giant open area. And in order to go in there, your cell phone, everything goes into a bucket before you go into the secure zone. Because if your cell phone was hacked, well, yeah, it can compromise everything inside of the secure facility. Yeah. So basically, yeah, red-black separation. Basically, secure stuff gets its own. Everything is isolated, so that the insecure stuff and the secure stuff are basically on completely different channels and things like that. Secure facilities, if the power goes out, they lock down. Most facilities, when the power goes out, they lock open, so you don't die, right? And so there's a lot of thought that has gone into secure and top secret and all this kind of stuff facilities. So if you're in a top secret facility and the power goes out, you can die. It could happen, because you get locked in. Because otherwise, what criminals would do is they'd come in and cut the power and everything unlocks, and you go in and take the stuff, right? So VANEC hacking is another name for it. Yeah, VANEC radiation. Yeah. So. Recent research has shown it's possible to detect the radiation corresponding to a key press event from not only wireless keyboards, but also from wired keyboards, and even from laptop keyboards. So, yeah. They bugged the U.S. Embassy. Oh yeah, that was a famous story. So the U.S. built an embassy in Moscow during the Cold War, and they knew that the Soviets would put bugs in, and they were ready to deal with it. Right, we'll just go through, do a bug sweep, pull out all the microphones and things like that, because the Soviets insisted they use Soviet labor. Like, no. If you're going to be building a big 5-story building in Moscow, you have to use Soviet labor. We insist. And so they built it, and then the people go through, the counter-espionage people go through, find these various bugs, but then they find out that the Soviets had pulled an extra super tricky which was they had embedded microphones into the concrete itself of the building. And so there were listening devices throughout the concrete structure of the building. And there was no way of getting them out without destroying the building. And so why go through all that effort? If you're trying to get nuclear secrets, you'll go to the effort for it, right? So what the U.S. had to do was build another embassy on top of the embassy that had enough of an air gap that the microphones and Tempest systems and things like that couldn't. So they literally brought in American contractors and built like a wooden superstructure on top of the embassy that was isolated from the rest of the building to do their stuff there. So yeah, this whole thing, like, it's just fascinating. So, yeah. Okay, all right. So let's. We got like half an hour left. We're kind of at the end of our topic here. I kind of don't want to start another topic. So, let's just do some exercises, maybe modular arithmetic. So I feel like we've been kind of light on that. So let's go through that. Let's go through some examples, because I'm going to give you guys the competency exam on modular arithmetic soon. Let's see here. All right, so here is a worksheet that I've used in the past. Okay. So, that's too long to say. Okay. So if you guys can do these one at a time, list 3 numbers congruent to 1 that are not 1 in the world of Z7. Just go ahead and type them on to Discord. You're sort of understanding division modulus. Good. Your brain has expanded then. List 3 numbers congruent to 1, that's the triple equals, that are not 1 in the world of Z7. Everyone's picking 8, 15, 22. There's an infinite number. You don't have to pick those 3. 50? Yeah, 50. Yeah, sure. Mm-hmm. Anyone else? $7 billion and 1. Okay, yep, for sure. 8, 50, 15. Okay, all right. You guys got it. All right, Z8. Calculate minus times 16 times man. Calculator can't handle it. Yeah, that's the idea. I like coming up with numbers that are so big you can't just like punch them into the calculator. They explode. Windows calculator's gone a lot better. They've actually added big int support basically behind the scenes. So it's gone harder for me to write questions. Because I don't want students just like brute forcing it. You know, it's like, I don't understand. I'll just let the calculator do it. That's not fun, right? So yeah, the answer is 0 because 16 in the world of Z8 is 0. So who cares what that is? Who cares what that is? Who cares what that is? We don't need to compute them because we are multiplying everything by 0. Okay. You guys understand? All right. In Z9, calculate 12 times 10 to the 2, 3, 4, 5, 4, 3, power. $12 in Z9? What is this 12 number you're speaking of? I have never met this man in my life. Yes, it is 3. Because 10 in the world of Z9 is 1. 1 to any power is 1. Remember, you don't modulus the powers. The exponent doesn't get modulus by 9. that because it's just how many times you multiply a number by itself, right? And so 10 is 1. 1 to any power is 1. 12 is 3. So it's 3 times 1 is 3. Okay. So in Z10, calculate blah, 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 minus blah, blah, times blah, blah. So 9 minus 4 is 5, right? Because when you modulus by 10, it's just the last digit. It's very easy to modulus by 10 in base 10. Just like modulusing by 2 is very easy in base 2. It's just the last bit. Okay, so 9 minus 4 is 5. 5 times 3 is 15. 15 modulus 10 is 5. Okay. In Z11, compute blah, 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 blah to the 10th power. I have no idea if that number is actually divisible, but I don't know if that number is divisible by 11 or not, actually. It might be. I should probably check, shouldn't I? Because it might be 0. Just assume it's not. You know, if I do something like that, it just means I just ran invalid input. Thanks, Windows Calculator. No, it's 2 digits too large for Windows Calculator. So we'll just assume it's not divisible by 11. It is 1, and the reason for that is it's Fermat's little theorem. 11's a prime. And so, because 11's a prime, if you raise anything to the 10th power, you get 1. And the reason for that is because when you're in a prime modular world, every time you multiply by any number, it does a permutation. And so, when you do 11 permutations, you get the original number again. So it'll go through all of them and go back to the original permutation. So if you're 1 less than that, it's like dividing by 11. So 11 divided by 11 is 1. That's another way you can think of that. That's Fermat's little theorem. It's pretty cool. All right, Z12. What is 8 divided by 2 in Z12? 4. Okay, that's one of them. This is not a prime modular world. There's more than one answer. 2. 2 times 2 is 4. I don't know. Is it? Negative 8? There's no such thing as negative 8. 8. 2 times 8 is 16. 16 mod 12 is 4. 4 is definitely one of the answers. 2 times 4 is 8. Okay. What you're looking for is 2 times your answer, mod 12 being equal to 8. There's only 11 possibilities. 6? No, 6 is going to be 0. So you want 2 times your answer to be equal to 8 in the world of mod 12. Can anyone find the other number? 10. Very good. 2 times 10 is 20. 20 modulus 12 is 8. Very good. 16. 16 does not exist. 16 does actually work, but it's bigger than 12. So 16 is the same as 4, the answer we had earlier. Okay. In Z13, calculate the multiplicative inverse of 8. So what number times 8 is 1? You can brute force it if you want. There's only 12 possibilities. 0 is obviously never the right answer. There's 12 possibilities. 8 times 8 is 64. 64 mod 13 is... Need more coffee. Let's see here. Programmer mode. 64 modulus 13 is 12. Nope. 8 times what is 1 in the world of Z13? There's going to be one answer. It's 13 is prime. By the way, there's only 2 answers to this one. The third spot is just a troll. Do you remember the equation to figure out the multiplicative inverse using Fermat's little theorem? Five. 8 times 5 is 40. 40 modulus 13 is 1. 13 times 3 is 39. 40 is 1 point higher than 39. You guys remember that? Because x to the y minus 1 power equals 1, then x to the y minus 2 power is equal to 1 divided by x. So it's the inverse. It's 1 exponent lower than the one we normally use in Fermat's little theorem. So that's a good one right there. So if you want to compute the modular inverse, you take y to the y minus 2 power mod y. And that'll give you the modular inverse. Only if z is prime. Okay, Z14, calculate 16 squared plus 2 times 12 quantity to the 14th power times 29. Anyone want to take a crack at this? Work through it in your head or work it on paper if you need to. I wonder if the pen will work. It will work. That's cool. So 16 squared is the same thing as 2 squared, right? 16 mod 14 is 2, so that's 4 plus 2 times 12. 2 times 12 is 24. 24 mod 14 is 10. So that is 14 to the 14th power times 29, which is 1. 14, however, is 0. 0 to the 14th power is still 0, times 1, still 0, so the answer is 0. Z15, calculate 1, 2, 3, 4, 5, 6 factorial. One times 2 times 3 times 4 times 5. I thought you had to modulus the factors in the multiplication. Left side here works out to be 4 plus 10 is 14. So this quantity is 14 to the 14th power. So the 14 doesn't turn into 0. The thing on the inside, the regular number, turns into 0. 0 to the 14th power, 0. 0 times 29, 0. Yeah, this one also is 0 because we're going to multiply 1 times 2 times 3 times 4 times 5, times 12 times 13 times 14 times 0 times 1 times 2 times 3 times 4 times 5. So, and Z15, calculate 199999999 to the 14th power. Fifteen's not prime. Fifteen's not prime. Is that number divisible by either 3 or 5? Nope. I guarantee you it's not divisible by 3. I guarantee you it's not divisible by 5. So as it turns out, it is relatively prime to 15. Okay. So is it divisible by 15? If it's not divisible by 3 and 5, it's guaranteed not divisible by 15. In order for something to be divisible by 15, it has to be divisible by either 3 or 5 or both. That'd be like saying something could be divisible by 30, but not divisible by either 10 or 3. Kind of weird. Yeah, so 1999, 4, 5, 6, 7, modulus 15 is 4. I don't know if that helps. Probably doesn't. The point, though, is that this number here is relatively prime to 15. So the answer is 1. It's a big number, 88 digits. Answer is 1. It's Fermat's little theorem, right? Fermat's little theorem is x to the y minus 1 power mod y equals 1 when x and y are relatively prime. So obviously if y is prime, it'll always be 1. But remember, this is why the primality testing, for using the Fermat's little theorem for primality testing, you have to do it on multiple numbers. Because it's a possibility you get 1 even if y is not prime, because they just might work out to be relatively prime. In this case, we know that 1,999,999 is not divisible by 3, because divisible by 3, any number divisible by 3, the digits all add up to divisible by 3. So all 9s would be divisible by 3, but it's got a 1 on top of it there. It's not divisible by 3, guaranteed. And it's not divisible by 5, because all numbers divisible by 5 end in a 0 or a 5. So, long story short, is just by eyeballing that, I could look at it and be like, 1,999,999 and 15 are relatively prime, therefore the answer we're going to get is 1. So, if we're doing a Fermat primality test where you do this equation over and over again to see if y is prime, it would give a 1. And so you'd have to try a different number. You'd have to try like 14 and, 13. If you try all of them, there's only 14 possibilities there. So let's try 14 to the 14th power, modulus 15. We get 1 again. What about 10 to the 15th power, modulus, 10 to the 14th power, 10 to the 14th power, modulus 15, typed in wrong, 10, at a weird angle here, 10 to the 14th power, modulus 15, we get 10. Okay, so for any number where they're not relatively prime, you're not going to get a 1. That's why you have to run these primality tests multiple times. If we do Miller-Robin, you need to run them 20, 30, 50 times, something like that. Okay. So the numbers only have to be prime relative to each other. Yeah, and that's why it's this test, you can't just do it once. You have to try a bunch of different x's. And if you get 1 on all of them, in this case, we'd actually test all the numbers from 1 to 14. And if all of them come up 1, then it's relatively prime to, not 1. 1 wouldn't work. I guess you could. Try all the numbers 2 to 14. And if you get 1 for all of them, then 15 is relatively prime to all of them, so it's a prime. Yeah. So in general, though, we'll run the primality test, 20, 30, 40 times, something like that. Okay. So 5 and 4 are multiplicative inverses in Z19, right? Because 5 times 4 is 20. So if you take 4 and multiply it by 5, you get 1. If you take 5 and multiply it by 4, you get 1. So they're multiplicative inverses. So what is negative 5 times 4? This will be our last question. We'll take off early today. What is negative 5 times 4? Not doing division. I mean, I guess we could do division. Yeah, so negative 5 times 4 is negative 20. Right? So negative 20. What is negative 20? How many times does 19 divide into negative 20? With a remainder of what? It divides in negative 1 times or negative 2 times? So, negative 20, a congruent number, we can just add 19 to it. Adding 19 to it is the same as adding nothing, right? And we can add 19 to it again, which is the same as adding 0. We get 18. So the answer is 18. As it turns out, you actually don't need to know that these are multiplicative inverses. It is a complete red herring. Okay. So, yeah. Remember, you can always, if you're in the world of Z19, you can always add 19. Does nothing. So that's another way of saying it's a congruent number. Okay. So that is basically what your competency exam is going to look like. I guess we got one more up here. Sunkist is a company that sells 10... whatever, it's too long to read. I'm done with it. Okay. So I'll throw up the competency exam on modular arithmetic tonight. It'll cover everything we've talked about so far in class. Modular addition, subtraction, multiplication, and division, and RSA. It's 4 questions, multiple choice. Answer 3 or better, and you get 100% on it. Don't get 3 correct, and you'll have to retake it a different version next week. And this replaces our midterm and final. Yep. Sort of understanding modular division. Don't worry, nobody, if we get a 3, it gets changed to a 4. Yeah, so you just need 3 out of 4. 75% turns into 100%. And if you get less, then you can retake it. And retake it until you are competent in this subject. Okay? Any questions? Is the review file the one you just put up? That is on Canvas, and I can throw up... I think it's on Canvas. Let me double check. Yeah, right there. Okay. Yeah. Worksheet number 1. We're going to start talking about hashing next time. Which is also modulus. Also modulus. Yep. No. So basically, if you run through it again, you don't know how to get an answer, just post on the Help Center. Feel free to give each other answers on it, because I mean, I literally just gave you all the answers. But if you have questions about how to work something out or why something turned out to be 1 all of a sudden, just ask on Help Center and feel free to give yourselves answers. Just not on the competency exam. Competency exam, yeah, no talking to your friends. You're free to use Windows Calculator. You're free to use online calculators. Just be aware that some of them are wrong when it comes to negative numbers. And they'll also overflow if you type in numbers that are big enough, which I tend to use. On that note, caveat, sometimes Canvas will scroll numbers off the edge of the screen. It's one of the downsides to using big numbers. And so if you're like on a touch interface or something, which I don't really recommend for taking a test, but if like make sure you swipe your finger and see all the digits in the number, there's usually some trick. I am not going to require you to actually do 100-digit arithmetic. You know what I mean? Like there's always some trick, some game that is being played there, and it's designed to sort of allow you to work with modulus just in your head and just very quickly be able to do modular arithmetic in your head, because it comes up in a lot of places in computer science. And so getting competent with it is just one of those mental skills that, I find to be very important. And that's what this class is about. This class is math for computer science majors. And so that's one of those things. So we'll pick it up on Thursday with hash tables, and that's it for now. All right, thanks guys, and I will see you next time.